Welcome to Brain Vision.
All right, so in this question, we're dealing with one of the previous examples in the textbook from much earlier in the chapter. We have a sphere at the end of a string, and the string goes over a pulley, and is attached at the other end to a vibrating piece of metal, and the sphere is suspended in water. In this specific instance of the situation. And in part A, we're supposed to figure out, this is just kind of building on the previous use of the example from earlier in the chapter. So we kind of start in the middle of things, and there's a lot of context that isn't necessarily established in the question. So if you're a little confused, go ahead and read through the example and see what they're talking about. But for this part of the problem, in part A, we are trying to find a formula that relates the radius of the sphere, r, to the number of antinodes in the horizontal portion of the string, n. And we want an equation for r that is dependent only on n and no other variables for part A. So just to start this part of the problem off, we'll go ahead and say that we are dealing the variables that we're concerned with are r, f, the frequency of the string, t1, the force of tension when the sphere is suspended in air, t2, the force of tension in the string when the sphere is suspended in water, and the length of the string. We'll spell water properly. The length of the string L, and the mu, the mass per unit length of the string. So this is kind of what we're dealing with in the first part of the problem, and how we'll kind of work our way through figuring out this relationship. So we can say that T1, where the sphere is suspended in air, is going to be equal to mg, where m is the mass of the sphere. And B, the buoyant force on the sphere when it's in water, is going to be equal to mg minus T2. And then we're also going to say that the frequency in the string, we're given two situations before, where the string is in the second harmonic when suspended in air, but it's in the fifth harmonic when suspended in water. But nothing else has changed. So we can say that the frequency f of the string in this situation is equal to n1, which is the mode when it's suspended in air, over 2L, which is times the square root of T1 over mu. And this comes from just taking the fact that when you take v divided by lambda times, and then you have multiplied by n, then you'll get the frequency of a mode of vibration in a string where that's under tension. V, of course, is square root of the tension force over the mu, and then the 2L comes from the length of the string and the full wavelength. We're also given, we can also say that this same frequency, f, is equal to, when we're dealing with this sphere in water, is going to be equal to n, which is the n that we're concerned with this problem, which is why there's no subscript, n over 2L times the square root of T2 over mu. And since these frequencies are the same, we can set these two equations as equal to each other. So we can say that n1 over 2L times the square root of T1 over mu is equal to n over 2L times the square root of T2 over mu. And we can go ahead and start simplifying this a little bit. We have 2L in the denominator on both sides and the square root of mu in the denominator of both sides. And what we're going to do is we're going to solve this equation for T2. So we'll go ahead and do that. So we can do that by just squaring everything. So we have n1 squared times t1 is equal to n squared times t2. Solve that for t, we get t2 is equal to n1 over n, and then square all of that, times t1. And we know that t1 is just equal to mg, so we can say that t2 is equal to n1 over n squared times mg. Now, what we do from here is we can substitute this formula into our formula for the buoyant force. So if we remember, we said that B is equal to mg minus T2. Well, now we have a formula for T2, so we can go ahead and substitute that in. So B is going to be equal to mg minus mg, or minus the square, or sorry, n1 over n squared times mg. We can simplify that to say that B is equal to mg times 1 minus n1 over n squared. And then all of that's in parentheses. Now, from here, we go ahead and we find another formula for B. And that is based on the shape of the sphere and the density of water. So we can say that this formula comes out to being that B is equal to rho W, which is the symbol I'm using for the density of water, times G, acceleration due to gravity, times 4/3 times pi r cubed. And the 4/3 pi r cubed, of course, comes from the volume of the sphere. So since we have two formulas for B, we can go ahead and set those equal to each other. So we have on the left side a rho W times G times 4/3 pi r cubed. That is equal to mg times 1 minus n1 over n. And then all of that is squared, and then close parenthesis. And now, so we're trying to find a formula for r in terms of n and nothing else. So we have an r cubed on the left side with a bunch of constants in front of it. So we can go ahead and bring those constants to the right-hand side and take the cubed root of the right-hand side. So we already have a g in both sides, so we can go ahead and just take that out first. And then we'll say that r is equal to 3m, because we have 4/3. We'll take the reciprocal of that. So 3m divided by 4 pi times rho w. We'll need a parentheses out the front here. And then, just checking my notes here, all of that is times 1 minus n1 over n, and that is squared. Close that parentheses, and close that parentheses. And all of that is to the 1/3 power, because we had the r on the left-hand side to the third, so we take the cube root of both sides. So that is a very complicated version of our formula, but now we can start simplifying it a bit, because we're told in this example that the mass of the sphere, m, is equal to 2.00 kilograms. And then we know that rho W, the density of water, is 1,000 kilograms per meter cubed. So we can go ahead and substitute those in. And we also know from the specific instance of the example that n1 is going to be equal to 2. So that actually gets rid of all the variables that we don't want, because we have 3/4 pi, which is just a constant, but we have m, which is taken care of, rho w, which is taken care of, and n1, which is taken care of. So this will give us, with some simplification, a formula for r, the radius of the sphere, in terms of n. So we'll go ahead and plug all those in. And so we get the equation that r is equal to 3 times 2.00 over 4 pi times 1,000. And then we have an open parentheses, and then 1 minus 2 squared, which is just 4, so I'll just go ahead and write it as 4, over n squared. And then we'll close that parentheses, make that like the same size. And then another parentheses here, which gives us the third root. So then if we simplify that first term out to the front, the fraction, the 3 times 2 over 4 pi times 1,000, that's also taken to the square root. So we can go ahead and simplify that part to be r is equal to, if you take 3 times 2 over 4 pi times 1,000, all of that taken to the 1/3 power, you should get 0.0782, and then all of that is going to be multiplied, or not all of that, just that will be times 1 minus 4 over n squared to the 1/3 power. And that is our formula for r in terms of n. So that gives us our answer for part A. But we're not quite done, we still have a few more parts. In part B, we're asked what the minimum value for n has to be for a sphere of non-zero radius. So, because I mean, obviously you can't have a negative radius, you can't have a zero radius, because then you don't have a sphere at all. So this is very simple. You just take a look at your formula and you start at 0 and go up until you get a value for r that makes sense. So if n is 0, then in the 1/3 power, well, you can't have n be 0 because they're going to have 4 divided by 0. So that doesn't make sense. That already breaks the equation. That doesn't make sense. But if you have n equals 1, you'll have 1 minus 4 over 1. So within the 1/3 power, you will have 1 minus 4, and then you'll take the third root of that. And so you will have you'll have 0.0782 times a negative number, and then your r is going to be negative, which doesn't make sense. We have to have a positive radius. So n equals 1 is out. And then we go to n equals 2. Then you'll have 1 over 4, or 1 minus 4 over 2 squared. So you'll have 4 divided by 4, which is 1. 1 minus 1 is 0. 0 to the 1/3 is 0. And then you have 0.0782 times 0. So then your radius is 0, and that doesn't work either, because we're told specifically not zero radius. But if we get to if we get to n equals 3, then you have 1 minus 4/3. 1 minus 4 over 3 squared. So 1 minus 4/9. You take the third root of that. That'll be a number, between 0 and 1 about. And then that's multiplied by 0.0782. And so that works. That's the first number that works. And as n keeps getting bigger, it'll continue to be a number that makes sense. So our first number that will create a sphere of non-zero radius is n equals 3. And that's our answer for part B. And then in part C, we want to know what the maximum radius of the sphere is. And so to do this, we go ahead and just take the limit of the equation as n goes to infinity. Because as n gets bigger, the radius of the sphere will continue to get bigger, as we've seen. So, because we started, when n was 1, we had a negative number. When n was 2, we had 0. When n was 3, we had a number between 0 and 1. So r increases as n increases. So we take the limit as n goes to infinity of 0.0782 times 1 minus 4 over n squared to the 1/3 power. And this is thankfully a very simple equation to do this with. As n gets very large, it's in the denominator of 4 over n squared. So as n gets very large, you're going to have 4 over a very, very large number. So that fraction 4 over n squared will approach 0. So then this equation will become 0.0782 times 1 minus 0 to the 1/3, which of course 1 minus 0 is 1, 1 to the 1/3 power is 1. So then this will just become 0.0782. And then our maximum, scroll down very far. So our maximum radius, our max, then becomes 0.0782 meters, or you can write that as 7.82 centimeters, either way. And so that's our answer for part C. And this will, the question asks specifically for, what's the maximum radius that will create standing waves? And that's the equation. That's the crux here. That's why we can say that n goes to infinity, because we need n to be some number for there to be, some integer for there to be standing waves. So that's why that works for here. And then in part D, we say that, we're asked what happens if we have a sphere bigger than this maximum value. And the answer here is actually quite simple, and that is that the sphere will float. And that's really all there is to it. At that point, we have a fixed mass for the sphere. So at that point, the radius of the sphere has gotten so large that the volume has gotten large enough that it is less dense than the water, so it just floats on top. And then this is also important because since it's floating, there is no tension force in the string. The tension in the string becomes 0, which means that standing waves cannot be created. And so that's why that happens. So yeah, that's how you do this problem.